I welcome you to this special tournament. Quickly to myself. My name is Sir Romano from the house of Roth. I am a mercenary from the kingdom of 𝗔𝗰𝗃𝗀𝗃𝗃. And as you can see, I have quite a lot of dungeons, also known as social media channels, where you can follow me on my journey through the infinite tournament, also known as DevOps. Quickly to today, in this dungeon here, which is sponsored by 𝗟𝘁𝗀, we will have the following torture for you. So first, we thought about some drinks, which we had, and then we have the welcoming, which we are in now. And then the first torture starts, which is the haunted DevOps, the spooky tales of seamless security in a cloud-native world, presented by Urs, where is he? Over there, and by Simon and Christian. After that, we will have a quick break because you need to rest a little bit after that torture. And then we have the second talk of Is Serverless a Blatant cost trap or just a trick? Presented by Lena, which is over there. Cool. After that, we will have a prize draw. You see the prize over there. It's the Millennium Falcon, which you can win, but you can only win when you have a costume. So we will ask you then to come to the stage, and by applause, we will vote for the best costume. Of course, those people who are presenting and those who are from the organizers will not be part of that. Yeah. Sorry. Okay. Today's sponsor of drinks and of the location is 𝗟𝘁𝗀. And I don't know, Urs, do you want to say something about 𝗟𝘁𝗀? Okay, later. He will say something later about 𝗟𝘁𝗀. But a big applause to 𝗟𝘁𝗀, which sponsors us here, because without 𝗟𝘁𝗀, this would not be possible. And you can see they really have a nice location. This whole dungeon is absolutely beautiful. So applause. And with that, to the DevOps Meetup Zurich. The DevOps Meetup Zurich is always looking for new speakers which could speak. So if you have a topic and you would like to present here, please approach me. And we are also looking for other sponsors. So if you also want to sponsor, and if you also have such a great location as 𝗟𝘁𝗀, please approach also me. And if you have just a topic in mind where you say, hey, this is a topic which we should talk about at the DevOps Meetup Zurich, then also approach me. And with that, we are coming to our first tournament or torture. Perfect. I hand over to you.
Cool, thanks. Can you hear me? And can you hear Christian?
Can you hear me? Perfect. I hope it's not a torture.
Yeah, thanks, Romano, for the great introduction. So actually, a very quick introduction to us. I'm new to the Halloween business, so I didn't prepare like such a very nice introduction about my person in the Halloween costume. In my normal life, I work at Open Systems for more than 10 years in different roles as an engineer, more recently as a product owner and product manager. And yeah, we're going to present the project that we have been working on, not for the last full 3 years, but we first started like 3 years ago with this cloud-native WAF. Yeah, as I said, I'm new to the Halloween business, and I must say I somehow managed to avoid Halloween for the last 10 years. And I thought I have a very good excuse this year again, and then you got me. But I must say, It's actually nicer than I thought. So that's about me, and my colleague Christian is going to introduce himself.
Hello, I'm Christian. I'm more the tech guy, and actually the platform we are also talking about tonight is 4 years old and not 3 years old. So a bit older, but yeah, you're right. The Airlock or the microgateway web application firewall is very new for us as well.
So what's behind the fancy title, seamless security in a cloud-native world? I mean, in the end, it's just transforming our VM-based WAF monolith that we had for the past 20 years into the new cloud-native environment we're building for 4 years. So yeah, what is a WAF actually? That was the question of a colleague that we gave this presentation as a test because he said maybe not everyone knows what a WAF is. Web application firewall, a WAF protects your websites, your eShop, your workloads you somehow expose to the internet. So it filters for malicious requests. It makes the application secure. Usually, application developers believe that they already developed the application in a very secure way, but the WAF then is kind of the second gate that makes it really secure, I'd say. Then about the WAF, then very quickly about open systems for the one that don't know it. 250 people in total, roughly 100 engineers. And what we do, we basically protect our customers from the evil in the internet, and we make sure that nothing comes into a company network and nothing leaves the company perimeter. Customers are usually, I don't know, Swiss insurances company with like 200 branches around the world, and we connect them all together, make sure the exact same policy is deployed in all branches, and so on. And I mean, that's the business part, but behind that is a huge technical stack, of course. Then what we protect and why we need this web application firewall. These are our assets. We protect an IDP that we expose to the internet, several APIs, and then our customer portal where our customer manage the service they get from us. And then what we do as a team.
Yes, I'm a part of the platform team. We're called OSDP, that's our logo, and we manage and build kind of the Open Systems internal cloud platform where developers deploy stuff on top. This is kind of how it works, basically, or how it looks like. It's multi-tenant, it's a multi-environment, multi-cluster, and soonish multi-cloud provider. We use namespaces to segregate kind of use cases. And what we do is whenever someone wants to deploy something on our platform, they create a product, which is very simple to create. It's basically an Microsoft Entra group, where all developers or the application gets access to, and all access to kind of Kubernetes, but also to other cloud-native services is based on this product. A bit more details, lots of logos. If you are familiar in the cloud-native landscape, you know some of them. Via a product, you get access to a namespace, you get access to a path on GitHub where you can deploy your code. You get CI/CD, we use Argo CD for that. You get access to secrets from within your various Kubernetes clusters, but also from outside. You get access to serverless. Actually, I'm interested then to hear how much it costs later on. Then we have a message broker, telemetry, monitoring, alerting with Grafana, alert manager. You get cost control, which is also very important in a cloud environment. And we also provide lots of kind of cloud native services like storage, various databases, and a data science kind of setup for our users. To the whole part on the top right, which is ingress from clients connecting to services we provide, we come later. So now before you saw kind of the platform, all Kubernetes, all pretty modern, pretty standard. And this was how it used to be. Like on the slide before, you didn't see a web application firewall. So services we exposed publicly, we still had kind of in the old environment, which looks much simpler and which looks like this. In the center, you have, we use Airlock Gateway from Ergon, which does TLS termination, rate limiting, AAA, load balancing, header sanitization, all those web application firewall stuff, and deployed on VM or bare metal and deployed in 2 data centers. And then on the back end, you have also again VMs or physical hardware where actually the application is on. And we had to find a way to deploy what we have here on our new platform. And
yeah, I mean, if you look also a bit in the past, how like processes looked like and how different teams work together. So if you look at change processes we had and in the old landscape with the WAF, we basically had 2 main actors, like the security team that owned the WAF, that operated the WAF also, that did all the policies for the WAF and so on, and then the service team that developed application and hated the WAF, basically. And why they hated it. The change process was a bit complicated. So development team, you can see this on the blue person here. They developed the application, then they wanted to expose it to the internet. They had to define some filters and policy, what kind of HTTP requests are allowed and whatnot. And then they basically created some kind of pseudocode, opened a ticket. This ticket was then picked up by the WAF team. They implemented some filters somehow, logged into the Airlock Gateway WAF UI, deploy. I mean, maybe had a question, so went back to the ticket, asked questions, was back and forth, and in the end, manually deployed this WAF change. And then the development team like could test the change. But this was usually, I mean, sometimes it took half a day, sometimes it took multiple days. But it was always like a lot of interactions. And yeah, I mean, people didn't really like to work this way. So when we started, we basically started first building the new platform, and then the WAF was just a component much later, right? I mean, first the foundation, then at some point later you also take care about security, and then we were running this Kubernetes cluster and the platform, but with the WAF gateway in front of it still running on a VM. So when we started to build this platform, we also agreed on a no VM policy, and I mean, Airlock Gateway was still running on a VM, so we had to find a way to do that differently. In the meantime, also team structures were organized a bit in a different way. The security team that we had for several years was changed a bit with a different focus. Yeah, then we had the WAF gate, the Airlock Gateway was running on the VM, so we had to do like yearly failovers that people didn't really like because they need to happen on weekends, and a non-intuitive config management, missing integration into the observability stack, and so on. So we basically summarized that with like unclear ownership and responsibilities, and then the missing platform integration. So that was basically the starting point the problems, the pain points we identified. So we came to the conclusion that needs to change, and we looked into.
Yeah, we created highly simplified, basically a wish list, what we want to have from a new solution. First of all, it had to be GitOps to support self-service. It had to be scalable, not only in a technical way, but more importantly in an operational way. It had to support those kind of cloud-native aspects, container-based, and it has to run on our platform. We use Istio heavily, as Service mentioned, also as ingress gateway. Then we looked at the various projects or solutions. Here are only a few of them, Kubernetes native ones like 𝗬𝗱𝗏 or 𝗬𝗏𝗏𝗏, which you deploy yourself. We also looked at SaaS services, Azure 𝗲𝗏, Cloudflare 𝗲𝗏, I don't know the name again. However, none of them kind of gave us the flexibility or the functionality we needed to kind of operate the way we operate our platform. And yeah, there was a new tool on the horizon, and you can guess it. It was the Airlock microgateway. It was not officially out when we kind of started to look into it.
It was actually in the previous version out, like version 2, and it was horrible. But then we learned that version 3 is coming, which was like a change maker. No, I mean, it was really a change.
And yeah, why the microgateway, it gave us a good integration into our platform or Kubernetes platform. It supported Istio, which is for a tool that looks at the traffic on this level, quite important. And what 𝗟𝗏𝗏 did very well compared to kind of the Airlock gateway, to configure the microgateway, they used custom resource definitions. So this allowed us to do configuration, GitOps style, self-service. It was easy to do policy enforcement, which was not possible at all before. And there are also kind of personal reasons. 𝗟𝗏𝗏 is local, and we have a long-standing partnership because we use Airlock Gateway for a very long time. 𝗟𝗏𝗏 has a trusted security vendor posture, I would say, and that also comes with easier discussions with compliance. And yeah. This brings us kind of to the present, how the setup looks now. This is how, simplified again, we deploy the microgateway. You see on the left side, again, the clients, be it internal clients which connect to the services via one, can also be external clients via public internet. They land on an Istio ingress. Istio ingress does TLS termination, rate limiting, authentication, and load balancing. So as you can see already, the microgateway, the way we use it, does not support the same features, or we use only microgateway to do HTTP filtering, while we use Istio and our service mesh to do kind of ingress stuff. And then the traffic goes from the ingress to the sidecar on the Istio sidecar on the top left. This part does authentication and is encrypted or decrypted and handed over to actually the microgateway, which then does all the HTTP stuff. Header, sanitization, content filtering, schema validation, and so on. And only if all of this say, well, it's valid and it's okay, traffic is handed over to the app container. Yeah, and with this setup, it works in a way, if you remember again, how we do products separation of products by namespace. It allows us to kind of take management of the 𝗲𝗏 from a dedicated team and give it back to the developers. So this maybe if you use Airlock Gateway, you know that's how you configure the Airlock Gateway. It's a UI. It's a very complex UI. It's a lot of things to click. It's hard to configure. It's hard to copy config from one backend to another one. It's hard to maintain, hard to track changes. Mistakes happen. And this is how the configuration now looks like. For Kubernetes or YAML engineers, it's easy to see. It's a lot of text, but actually it's quite simple. On the left, that's kind of our own setup, how you configure ingress. And on the right side, you see actually a very simple but working example of how you configure the Airlock microgateway. And with just this here, you configure exposing this service 𝗬𝗬, which is in the namespace 𝗬𝗬𝗏𝗏, to the public internet, to expose it within the WAN. DNS is set up, routing is set up, certificates are set up, and a microgateway policy is created, which with a special deny rule for, I don't know, /API. Yeah. So for us, this helped a lot. And here is how we do config deployment. A developer writes a config, pushes it to Git. It's only accepted if some policies match. As soon as it's merged, the config is pulled by Argo CD and deployed into the namespace of this product. And then it configures ingress, microgateway, /ISTIA sidecar, and everything necessary to expose something publicly. So yes, compared to before,
it's more self-service.
It's much more self-service.
So if you look at the process side, again, we have an additional actor now. You remember we had the security team and the service team before. Now we also have the platform team that owns the platform and the WAF component. Then we still have the security team that defines policies on a very high level. For example, something super simple, workload that is exposed to the internet through Istio must have a filter policy somehow. And then on the right side, we have the service team still that owns the application, but at the same time also the filter policy. So what does that mean for a change? Compared to before, you also see here there's only one actor involved. I mean, there is no back and forth anymore between different teams. Developers can work independently. They develop the app, define the filters, policies get checked automatically, filters get deployed automatically through the robots, and then in the end you can just test the change. And I mean, like efficiency-wise, I mean, it's much faster. Before we talked about days, and now we talk about minutes, basically. And I mean, we had several nice side effects as well. I mean, certificate renewal process, for example, was horrible because there were even more people involved. There you had an IT team internally at Open Systems that reached out to SwissSign, getting a certificate via ticketing systems. Then the CSR was wrong several times. It's always copy back and forth. And now, yeah, we're using Let's Encrypt. I mean, something like that could have been introduced already with the old platform as well. But I mean, as we did this renewal entirely, we took the opportunity to improve several processes. Or then we have DNS, for example, that works much more automated now. We don't have the yearly DC switchover anymore that we used to have before, and so on. So a lot of automation is involved, and engineers have more self-service. And I mean, yeah, to summarize that, automation I already described with the certificate, for example. Christian mentioned like the CI/CD, GitOps processes, configurations get deployed automatically. The microgateway can be easily updated with the platform that we have, and all the teams are much more independent because they still collaborate with other teams, but they can focus on the work they need to do, and they don't need to reach out with a lot of dependencies. And also there was a bit of a cultural shift in the sense of, I mentioned in the beginning, in the past, the WAF was this black box that nobody really liked. And now, because it's also cloud native, people start to understand and they say, yeah, okay, a WAF, yeah, makes sense because I know what I do. I can do it myself. I mean, easy. Let's do it. So much less discussion in this regards as well. From a security team perspective, on the other hand, they were a bit worried that they have to like get out of the game and give over the control to the platform team to a certain degree and not be involved in every change anymore. So not doing micromanagement anymore, but that they can do like high-level policies where we make sure from the platform team that they are applied and everyone is still compliant. Yeah, so developers are happy. We have more self-service, and that's a perfect opportunity to do a quick advertisement break. So if you like all that stuff, we're also hiring. We're actually hiring a platform engineer right now, so it's not just HR bullshit talk. Yeah, if anyone is interested, or if you have a colleague, then talk to us. That's about the advertisement. Then, yeah, lessons learned, back to microgateway, new tech stack, new principles. I mean, microgateway works completely different. So if you want to go into this journey, forget all you know from Airlock Gateway and be ready for a new tech stack, new technology. I think this is just I mean, we saw that with many other products as well. I mean, this is basically how this transformation from the old or VM-based or hardware-based into the cloud-native-based world works, I'd say. And I think what is special in this case, find the right tool for the right feature. I mean, Christian showed it before. Basically what Airlock Gateway did as a monolith before, we have now separated into Istio and the microgateway. So, I mean, there are some tasks that Istio does, like TLS termination and other stuff that the Airlock microgateway does, like filtering. And I mean, don't look for feature parity in the very beginning. I think that's also a discussion we had with some people not being yet in this new world. So yeah, but I mean, from our gateway, I know this isn't that feature, and I saw this is not yet available for the micro gateway. So I mean, can we really use it in production? And I mean, yeah, what's the point here? I mean, find out what you need, and then you have the list. If you can check all the features you need, then you can go. Yeah, and then very quickly, pros and cons from our point of view with Airlock microgateway. I mean, what we really like is that you have a faster development life cycle compared to since we started. I think that's really cool. Then, as we already mentioned as well, the local partnership is super cool. That's something we really appreciate in general. We have many partners, but collaboration and mindset and so on is just easier with the locals one. Christian mentioned as well, the platform integration is really nice. I mean, it's really the product we have envisioned when we created the wish list, and you made it perfect. And also the support was nice. What we like less, I guess this is more like a philosophical topic. It's not open source. It's probably the only open source.
The only one.
The only product we're running, which is not open source. We run other products where we have an open source product we run, and then we buy support. I mean, we totally agree and believe that, I mean, you should make money somehow with it, but open source comes with the advantage that you can contribute, that you have like a transparent they have transparency with open box and ongoing development and so on. So that's what we really like with other projects. And observability, not missing, maybe it's a bit unfair, but there's a bit room for improvement still. And with that, I'm handing over to Urs, actually, who's going to give you a bit more insights in the product.
Thank you very much. So, thank you. Oh, I chose to wear a hat so all of you can see me. So there is just one part of news. I mean, I hope not everybody of you hope to get away without any marketing slides today. That's my job right now. I'm pre-sales at Airlock at 𝗟𝘁𝗀, responsible for part of my job is microgateways. So I'll give you a few news about what happened in the last few weeks. And one is actually brand new. A new version of the container, the microgateway landed actually just yesterday, version 4.4, and it brings a few enhancements. Okay, first off, I mean, you heard a lot about technology and that they use sidecars, as the sidecar is injected into the pod to protect the application. Now with the newest release, you can have the option of choosing a different way of deployment, more like similar to what we had before with the Airlock gateway, which was a standalone and shared by different applications. So you can have something similar, but it is still within the container, within the cluster. And we make use of Kubernetes Gateway API for that, which is slated to replace Ingress over time. Today, we have core conformance with the standard. We are not yet suited to really replace Ingress functionality, so being placed at the edge of the cluster and taking all the packages, the traffic in. That will come in a future release. Then you will be able to choose whether you want to have the same component directly as an Ingress or not. But you will not be forced to do that. So if you have your own preferred Ingress component, you will still be able to do that. Okay, the other part that I'm going to highlight, the other new feature, is that the Airlock microgateway now has an inbuilt OpenID Connect relying party component. So you can do upfront authentication. You can easily control whether or check whether a correct token is included in the request. And if it's not, then you hand it over to an OIDC OP to do the authentication. And obviously it will be coming back and you exchange the authorization code for a token, for an ID token, access token, etc. And then you don't have to handle that within your application. You also don't have to use the OAuth 2 proxy anymore, which I heard was pretty hard to maintain and operate. So this is all built into this component and helps you do that. By the way, we have a lot of experience doing OpenID Connect with our other components, Airlock IAM, etc. So just one other information, if you think, okay, that could be something I want to look at, there is a community edition. Yes, it is not open source. We are looking into that, but you can understand coming from, like, we do this business since 1997, and with this legacy, it's not easy to change into an open source model. So we have to think about that carefully. But there is a community edition, which you can use for free. It is functionally fully complete. It has all the possibilities that you want, but it is operationally limited. So it supports, or it handles 5 requests per second at max, and it supports a limited number of pods. I don't remember the number exactly, but I think it's 5. Okay, and then I promised a few words about 𝗟𝘁𝗀. Who are we? For those who don't know us, 𝗟𝘁𝗀 is a Swiss software development company. We do custom software development. That's actually like 3/4 of the company. That's their business. They're actually working in this building here. And the part I'm coming from, Airlock, we are like about 200 meters away in a different building, and we are a subsidiary of 𝗟𝘁𝗀 focusing on security products for web applications. Now, these are the services that 𝗟𝘁𝗀 offers to you. Well, yes, we started with software development, custom software development, but we also do ideation, consulting, strategy consulting, and we also, for some of our customers, we operate the solutions that we actually build. If anybody have the rest of that, let us know. With that, it's time for a break.
So, hello also from my side. Welcome, friends and future friends, to this very clickbaity talk. How many of you have heard of Bedridge's Law? So that's a law, kind of like Conway's law, and it says that every article or every kind of talk or blog post, which the title is a question of, the answer to that question is usually no. We will see if that also applies in this case, especially now since it's an either-or question. It's not so easy anymore. Also, there will be lots of charts, so I hope you like charts. If not, bad luck. To introduce myself, my name is Officer Jenny. You might know me from Pokemon. I'm a police officer in 𝗟𝗫𝗂𝗃𝗃𝗀𝗃𝗃 city, 𝗟𝗫𝗂𝗃𝗃𝗃𝗃 city. My hobbies are driving my motorcycle around town and arresting people for mistreating their Pokemon. Now, you might be wondering, why the hell am I listening to a policewoman talking about tech topics? And you're right about that. But my hobby is that I also work at a small company called Bespinian. Bespinian is a small IT engineering company from Bern. We're 13 people at the moment. And what we do is we help our customers to make their applications more cloud native. So we help them choose the right cloud provider. We help them migrate their applications onto there, being very hands-on, doing automations, rewriting the applications to make them more 12-factor, and all these kinds of things. But now enough about that. The motto of this talk should be "Talk nerdy to me," which in this case means two things. So one, if you have questions at any time, just shout them out. I won't be offended if you interrupt me or anything like that. I won't arrest you, don't worry. And the second thing is that I wanted to ask you, who of you is already running a serverless application in production? Okay, you people. I hope it's still worth that I'm holding my talk here, because the goal of this talk is that we don't want to land here. So I don't know if you know this website, or it's actually just a small blog called Serverless Horrors, which is very fitting for today's theme. But it's people talking about their serverless applications costing much more than what they actually initially anticipated. And we see some examples here. There are some not so bad examples where it was just really surprising for them. But yeah, spending 300, $100 might be okay. And then we see some more horrible examples of people spending 120K on serverless stuff that they didn't really expect. And our goal of today is that we don't need to write a blog post here on this blog. First, quickly, since only some of you are running serverless in production, I wanted to delve into what serverless means, at least to me. It's kind of one of those bullshit bingo terms also. So I'll just give you a definition and we will stick with that. So for me, serverless means everything where you don't need to take care of servers. Obviously, there are still servers involved. They're just way down the hood. They are abstracted from you as an engineer, so you don't need to care about them. This can mean two things. On the one hand side, we have function as a service, or FaaS, which is what people usually think about when they hear the term serverless. Now, these are things like AWS Lambda, like Google Cloud Functions, like Azure Functions. It can also be stuff like Knative on Kubernetes. But usually that's what people think about. But also what we should think about is what I just call backend as a service, or BaaS. So any kind of service like S3 storage, like a completely managed database where I don't need to take care of the scaling of the different database shards or instances, all these kinds of things, really anything where I don't need to take care of servers, where I don't need to take care of the manual scaling and all these kinds of things. Also, serverless applications or services usually have something very important in common. They are very much pay as you go, which means that, for example, on AWS Lambda, if your function runs for 112 milliseconds, you're only paying for those 112 milliseconds. Even if your app is completely idle for the whole rest of the year, you will only be billed for those 112 milliseconds. And the same goes for other serverless services, like the ones that are in the backend and so on. And this is a very important trait because it can be a very big advantage for you if you have stuff where you know the access patterns and you know they're not going to be too big, or there might be very spiky in some cases, and then there won't be any load for the rest of the year, then you can really use this to your advantage. But obviously it can also be dangerous, because then usually you pay a bit more per millisecond than you would pay for just having something running constantly with the same load. Now, let's look at an example for that. First, we want to have a look at a compute example. As I said, there are different providers for this. We will today just take AWS Lambda as an example because it's the platform that I personally know best. But the concepts that we look at today, you can basically port to any of the providers because they're always the same. So if we look at AWS Lambda, the pricing for this is in a kind of simpled down version, is that you pay for the amount of requests that are coming into your function, or kind of the amount of events that it handles, and the memory times time, or what they call gigabyte.
Price on is number of requests.
Assign your function a certain amount of memory, let's say 1 gigabyte, and you pay for this amount of memory per millisecond that is being used. So it's kind of quite linear in terms of how much resources you give to the function, but also how long it takes to run. And you pay a kind of a fee for each request that comes in. If we compare that to Azure functions, it's exactly the same. As I said, they're quite comparable. Now, Google Cloud Functions, they recently introduced, they were acting in a very similar model, but they recently introduced a pricing that is a bit more flexible. So there you can have you pay for the gigabyte seconds of memory on the one hand side, and then for what they call gigahertz seconds on the other side. And so you can kind of scale the CPU and the memory independently, because that's quite important to know for the other platforms. For Lambda and Azure Functions, when you scale your memory, you're actually scaling the whole resources that your functions get. So you're also at the same time scaling the vCPUs that it gets, and you're also scaling stuff like network I/O and like disk I/O. More of a flexible pattern where you can scale that. This just as an example, kind of a couple of examples of what you would pay on Google Cloud Functions. And if you were to calculate those numbers, you were to see that it scales very linearly. All right, but enough of the dry theoretics. I'm already seeing a lot of faces like this because you're all very eager to dive into the numbers and into the charts. So let's look at a first one. So here, to really try to kind of compare the three platforms and to see what the pricing structure of such a function looks like, I took an example and made some calculations. Now this is all available. I did all of this in a spreadsheet and made a chart from it. So if you would like to have access to the numbers, please let me know. Also, it's important to be aware that this is kind of a very simplified model. So the pricing of these functions, there could also be other things added to what we just talked about, like stuff like ephemeral storage, or if you want to have reserved capacity for your functions, stuff like that comes on top, but we're ignoring that for now. Also, all of the prices that I did are based on the Frankfurt regions of the different providers, or Germany regions, to make them a bit more comparable. But what's actually important or interesting about this chart is that we see that all three cloud providers, or all three big hyperscalers, they kind of look very similar. We can't even really see the Azure line because it's kind of hidden behind the AWS line because their pricing structure is so similar. Also, what we see here is that they have quite generous free tiers for these applications or for these services. So you see here all the way up to 1 million requests, we don't pay anything. And that is because, for example, on AWS Lambda, they have a free tier of, I think, 1 million requests per month with a certain configuration of gigabyte seconds that you get for free. So that can make it even more attractive for like startups or for smaller applications that you only use several times a month. And then after that, So here on the chart, you see we kind of hold the amount of gigabyte seconds steady, but we scale the amount of requests that come into your function per month. And that's what you see on the x-axis. So this number here is the amount of requests that come in. And on the y-axis, you can see the price that you would pay for that. And you can see here with this configuration, the first 1,000,000 requests would be free on all platforms. And then on AWS, you would pay a bit for, and Azure as well, you would pay a bit for
gateway at the edge.
There you have, you pay per 1,000,000 requests, just as a standardized fee. And that's why we see this sort of steps pattern. Also, what's interesting is that the Google Cloud pricing looks a bit different because they actually have a free tier of 2,000,000 requests. That's why it only starts scaling there. And then on the right-hand side, we can see that all of a sudden we have kind of a hockey stick and it starts going up. And that's actually where we have used up the free tiers of gigabyte seconds. And from then on, you can see it scales very linearly. So yeah, as I said, this is kind of a made up situation, but it pretty well reflects how the pricing is made up for these kind of applications, and that it's very similar for all of these different cloud providers. Now, if we do the opposite, meaning we keep the number of requests steady, but we scale the amount of resources that we devote to our function, then you can see a very similar pattern. So here first we have the free tiers. Once we have used those up, we can still a bit use the free tiers of the of the number of requests, and from then on it scales very linearly, and also all three providers are very similar. So that's kind of the most important thing to take away from here. As we said, everything is pay as you go. And if we have a look at the same patterns at not compute, but something like storage. So in this case, I compared the different blob storage operations that these providers have. So that's AWS S3, Google Cloud Storage, and I think it's called Azure Blob Storage. Here we see again a very similar pattern. The prices are all made up by you pay per the amount of data that you have stored over time, and you pay for your read and write requests. And if we compare those three again, we see a very similar pattern. Here we don't actually have free tiers that are significant for the calculations that I made. Also, because you have to be a bit careful, sometimes the cloud providers give you free tiers that are only valid for a limited amount of time. So say only in the first year you get some free stuff, and afterwards you don't. And these free tiers I completely didn't take into my calculation. I only took the ones that you have forever. But here, very similar pattern. So we're scaling on the x-axis the amount of data that I have stored, and on the y-axis the price. And you see it's very similar again. We see that Azure is a bit cheaper than the others, but then if we look at it from the other side and we scale, we keep the amount of data stored linear, and we scale the amount of requests, then we see that Azure is more expensive. So kind of, they make it hard to compare each other to each other. We see very similar patterns. But so far we haven't actually really answered the initial question, right? We haven't really compared serverless with other compute models. We have just compared the different cloud providers. So now let's get into that. So we're going to take AWS Lambda again, and we're going to compare it to two other models of compute. One of them is called Fargate on AWS, which is a managed container service. So there you get just your container, it's fully managed for you, but it is usually running over time, so it doesn't scale to zero, or at least not as quickly as, for example, a Lambda function does. And we're going to compare it to sort of the more traditional world of just having a VM that is lying around, whether you use it or not. And here, again, with made-up scenarios, I just took a basic application that I made up, and then from sort of my experience, I tried to calculate how much resources it would use. And there we see a pattern like this. So again, on the x-axis, you would see the amount of requests coming in. And then for this application, I just took some assumptions on how many container instances it would need to serve those, how many VMs that would it need to serve those. And obviously, you can see the pattern that we expected. So the Lambda function scales very linearly, or completely linearly, actually. And for the others, we sort of have these steps when we have to activate our next instance, when we kind of have to scale out. And here you can see this pattern that I described a bit at the beginning, that over time, the more and more you use your serverless applications, it can actually become more expensive than just using your normal instances, which again, as I said, makes it very important to know the access patterns of your application beforehand. If it's a very steady access pattern, or if you have high loads, it might make sense to use something like a long-running container or a VM. And if you have very irregular access patterns, or if your application is at the beginning, if you're a startup, you don't have many requests, many users, it might make sense to go for serverless or something like function as a service. So like anything in IT, it depends. But now we looked at how these different things compare. But what if we actually want to get the benefits of serverless, but want to kind of keep these costs in control so that we don't land on the serverless horrors page? Some things that we can do to sort of optimize the costs of our function are that we can choose, we can usually choose different CPU architectures, which can make quite a big difference in terms of the price. On AWS, for example, you pay about 25% less if your application is based on an ARM architecture rather than an x86 architecture. Some other things that you can do is you can use stuff like compute saving plans. So if you already know that you're going to run your application for the next 3 years, you can buy capacity in advance, even for those serverless services. And then obviously they will give you a discount. And by doing so, you can save up to 70% in the costs that your application has. You can use more performant languages. There are quite big differences in how much time it takes for your application to run if it's written in something like Python versus something like Rust. And there again, you can get a lot of cost reduction because just your application is going to use less resources and is going to take less time to run. Another thing that you can do is reuse connections. So usually when you run one of those functions, the time that your function takes to start up, to kind of initialize the environment that it runs in, and to load all the libraries and to initiate connections and stuff like that, you usually don't pay for that part. You only pay for when your function actually handles the request that comes in. So what you should do is defer as much as possible of the work to these initial steps where you don't pay. So stuff like TLS handshakes and all these kinds of things. And by that, again, you can save some costs. Also, usually it's worth to kind of do tree shaking or to remove unused dependencies to reduce kind of how big your application is, because again, it takes some time to get your application started. Now, what can we do to cap the costs? Now, we talked a bit about how to reduce the costs, but still, if you have enough requests coming in, the costs can explode, right? And so currently there are, in my view, two things that you can do. One of them is you can set a billing alarm. So you can say, for example, if the costs for my function exceed $10 a month, then I want to be alarmed, I want to get a Slack message, I want to receive an email, or you can even then automate that it sort of turns off or limits how much your function is being used. Or what you can also do is you can limit the concurrency of your functions. So usually the concurrency that you get is you can have up to, for example, 1,000 functions that run at the same time. If you have 1,000 requests that come in at the same time. And you can reduce the limit of this concurrency to say 100 or even only 10. And then over time, you will have less costs. Another sort of cool thing that I discovered is this tool that is on GitHub. It's called AWS Lambda Power Tuning. And that's what I quickly wanted to show you. I'm going to take my badass gloves off for that because it's a bit hard to type. So this project, as you can see, is oops, sorry, the scaling is very big. So it's this product on GitHub, and what we can do is we can compare different configurations of the functions that we have made. So here again, I'm just taking the example of AWS Lambda, and I have deployed a function that is just called Fibonacci. And here you can see its code. So it's just a very simple Python function that calculates a Fibonacci sequence. Sorry. Just to put some load and for it to take some time to do these calculations. Now, you might wonder, what is the optimal configuration for this function? Because as I said, you can now tune the power, meaning that you can turn this knob of increasing and decreasing the amount of memory and the amount of resources that you give your function. And by that, either the time that your function runs will increase, or the amount of resources that it uses per time will increase. And you sort of have to balance it out in order to have the right amount of, or the least amount of costs, right? And this Lambda power tuning tool helps us to do that. So it's deployed into AWS as a step function state machine. If you don't know what that is, don't worry. What it does is it's just an application that is, again, also serverless, that is deployed here and that I can run. And when I run it, I have to give it some parameters. And here, the parameters look a little bit like this. So I give it the identifier of the function that I would like to optimize. Then I give it different power values that it should try. So in this case, I'm telling it try 128, 256, and so on, megabytes of memory that I want to give the function. And the num is just the number of times that it's going to try it to actually have a statistical significance. Or should I? Don't need, because my function that calculates a Fibonacci sequence doesn't take a payload. The identifier of the function is what you find here. So this function rn is the identifier of the function. So I'm going to copy that into this tool. And then actually do a run of this power tuning tool. And now the cool thing is that here you have kind of a live view of what the power tuning tool, that's a tongue twister, does. So first it initializes, and then it branches out. So it now takes all of these different configurations that I gave it, and it runs my function with the payload that I gave it 50 times with each configuration. And each time it checks how much time did it take for my function to run, and how much costs did incur due to that. It's going to take about a minute or so to run, and afterwards it's going to clean up, and it's going to give me a URL that I can then call in order to see the results. So for us not to have to wait a full minute, I'm just going to cheat and take my example. So this is from exactly the same function. This is what we would see after 1 minute. And as you can see, it gives me this simple chart where the blue line is the costs that occurred for this configuration, and the kind of reddish, purplish line is the execution time. And on the x-axis, you can see the amount of resources that it gave my function. So these are the values that I had configured in the payload that I gave the tool. And now we can optimize, right? We can now say, I want to optimize for execution time. There, obviously, usually it's better to give it more resources, and then the execution time will decrease. Or I can say, I want to optimize for costs. And there we can see an interesting pattern, because the lowest point of costs is actually not when I give it the most or the least amount of resources, but it's somewhere in the middle, where there is this golden middle where it takes quite little time to be executed, but I also don't have to give it the full amount of resources for it to be as fast as possible. So if I wanted to optimize for costs, then I would in this case give it 512 megabytes of memory. If I wanted to optimize for execution time, I would of course give it as much memory as possible. What's also quite interesting about this tool is that it has this compare button, and I can use this to then compare different functions even. And that's quite interesting because you can see, oops, sorry. Here you can see I had this Fibonacci function, right? But I actually also wrote the same function in JavaScript, so running on Node.js 20. I also have the same function down here running on Python 3.12, because the original one was running Python 3.11. And somewhere up here, I have the same function running on a different CPU architecture. And now I can play around with this, right? I can see how much cost benefit do I get from different configurations. I can then optimize these different functions and compare the different charts to each other. Now, so you don't have to watch me click around this. Gonna cheat again and show you what that would look like. So here we have those 4 different configurations that I just talked about, and you see that the patterns are always very similar. And I'm wondering why they're quite different from what we just showed. It's because we have more of a maximum configuration. So in this case, we told it to test actually up to 10 gigabytes of memory. That's why the cost explodes in the end. But we see that the patterns for the same functions are all very similar, but we see that's probably hard to read for you, at least from the back. We see that there are very big differences in, for example, the startup time. So here, this JavaScript function, even in the worst configuration, it took 140 milliseconds to run, whereas the Python example took 2 seconds in this case for a cold start. And we can also see the difference between Python 3.11 and Python 3.12. 3.11 took almost 2 seconds and 3.12 1.6 seconds. And if we compare that to different CPU architectures, we again get a different picture. So if you are in the case where you have to do power tuning to this extent, where you really want to understand your costs, where they come from, how you can optimize them, I can really only recommend this tool. But to close up, this is probably the most important slide of all. It's important to always think about the total cost of ownership when you're comparing those different platforms, right? Because it might be that by using Lambda versus something like Fargate and having containers running, you might save those $20 a month because you don't have your container running all the time. But if your team really understands containers and doesn't understand functions, then you're going to lose a lot of money by just your team struggling at the beginning, your team having to invest time to learn, and so on. So I would really recommend to also take these other points of costs into account, stuff like operations, stuff like learning that your team has to do, stuff like the lock-in effect, which is much higher when you're using highly abstracted services like function as a service, stuff like the tooling that you have available and that your team might already know. Usually that is much more than what you have on the bill that you get from the cloud provider at the end of the month. But it's very misleading, because the bill that you get at the end of the month is a specific number where you see exactly this costs that much. And that's why we can sort of have this fallacy that it's usually the cloud provider cost that we focus on, when it's actually stuff like that oftentimes costs much more. So I say this is the actual cost trap. And with that, I want to really thank you for your attention.